Hi, and welcome to our presentation. Our team has been working hard these past few months on Test Lab, a feature flag and A/B testing platform. Test Lab provides feature management infrastructure for the creation of feature toggles, rollouts, and experiments. We are so excited to share our project with you. My name is Abbie, and I'm going to get us started. As you can see on the map, we're spread across the US in different regions. I live on the central coast of California, near San Luis Obispo. Chelsea's up in Bellingham, Washington. Alison's in Harrisburg, Pennsylvania, and Sarah is near Salt Lake City, Utah. Besides being an all-female team, we're also united by a strong love of animals. Here's our plan for today. I'll start with an introduction to A/B testing as a whole, and we'll highlight some of the key challenges that exist within the problem space. Chelsea will take it over from there to describe the existing solutions on the market and what is unique about Test Lab. She'll give us an overview of Test Lab's architecture, and she'll describe and demo some of the key features of our admin user interface that provides good user experience for the developer who designs A/B tests. Then Alison will take over and dive into the backend. She'll explain the architecture and functionality of the API, the database, and the SDKs. Finally, Sarah will wrap up with a review and more detailed description of some of our key design decisions, as well as our ideas for future work. So what is A/B testing? Well, it's fairly straightforward to understand on the surface level. Let's walk through an example. You have a website, as seen here on the left, with a button. This is a super magical mystery button, and you want users to click it and not ask any questions. However, you're not getting the kind of click count you need. So you think of an idea, a great idea. You're going to give the people a reason to click. You present this variation to some users, and as you correctly predicted, when you add Ryan Reynolds pointing at the button, more users push it. You make the decision to roll this change out to the rest of users, and now everyone is happy. The key thing for A/B testing is that it allows for data-driven decisions based on real empirical observations. As another example, Google famously tested 41 different shades of blue for the color of advertisement links on their site. They presented each color to about 1% of their users, and they observed their behavior to end up choosing the best shade of a purplish blue. It may seem like a small detail, but it netted Google an additional $200 million in ad revenue. When well done, A/B testing can increase desired user behaviors and therefore also increase revenue. It also reduces the risks of a detrimental design choice based purely on a designer's preference rather than actual user behavior. The process of A/B testing is very much like the scientific process. The design team or developers form a hypothesis about how a proposed change will affect user behavior. Then they work to create those variations. Users are segmented so that each user experiences one of the two variations, and then their behavior is observed and that data is collected. As the experiment concludes, the team then analyzes the data and makes a decision based on the variant that performed the best with the users. A/B testing can go beyond simple design changes to the user interface. There are four main use cases. The most obvious are user interface and design changes, as described in the Ryan Reynolds example and the Google 41 Shades of Blue experiment. The simplest form of this is called what you see is what you get, where the tester can insert things or drag and drop elements onto the page without developer involvement, and the software itself generates the code. Next, the developers may want to test out new features or functionality, such as a search bar or a like feature. Third, there are many changes to the backend or hardware that an application can make, which may change user behavior in an unanticipated way. For example, some applications have users who are loyal and dependent enough on their application to tolerate the increased latency of less costly servers. Finally, an application may want to test out various third-party services or APIs, such as adding PayPal checkout. There are three main approaches to implementing A/B testing. The first and most common implementation is on the client side, which happens within the browser itself. The same version of the page is always served, and then the DOM is manipulated using JavaScript for users assigned to the test group. This approach is easy for developers or even non-developers to make experiments and test ideas. And there are a lot of existing services that perform this. You can easily and quickly test many changes without investing a lot of developer time. On the downside, the users in the test group will always experience a brief flash of the original page before a re-render of the test version. Also, sites that use libraries and frameworks dependent on a virtual DOM, such as React and Angular, will have the undesired side effect of misalignment between the virtual DOM and the DOM itself. The second implementation of A/B testing is on the server side. The code is modified on the server directly in the code base before being sent to the browser. On the plus side, this allows for greater access to user data, so segmentation based on certain criteria is possible. These testing platforms are generally custom built, which allows for more privacy and security. Server-side testing is a more powerful testing option, but the trade-off is that it requires more developer expertise and there are fewer third-party options. Finally, content delivery networks can be used to route users to completely separate paths. This is easy to roll out a change to all users, and it's ideal for static sites with none of the re-rendering concerns that we had on the client-side implementation. However, there is no access to user data, so there's no real way to curate user experience. Since variant assignment is random, in the worst-case scenario, you could also run into cache misses if one version is underutilized. Now we'll transition into some of the challenges that exist when trying to implement A/B testing. And then Chelsea will take over to compare some of the existing solutions and describe where TestLab fits in. There are four main challenges when it comes to actually implementing A/B testing that I want to discuss. First, there's that of consistent user assignment. It's essential that experiments can be designed so that the end users will always be directed to the same experiment or overall user experience. This is not only necessary for good user experience, but it's also required to have usable user behavior data for collection. The second challenge is to what degree the developers have to be involved in creating and managing the experiments. If the tools are too hard to use, that requires expensive developer time to implement tests that may not even see a significant return on investment. However, if the tools are too easy, the trade-off is that maybe the tests won't be very robust, or that the solution may not have as many options for full control and flexibility of use. Third, we have data collection and analysis. How are we observing and analyzing user behavior? Some testing services require an existing third party to be used for analysis, such as Google Analytics. Others do it all in-house. Again, there are options and trade-offs here, including data privacy and demand for computing resources. Finally, there's the question of statistical validation and proper experiment design. There are many factors involved in creating a good experiment, and A/B testing services may provide some safeguards to guarantee for a valid and proper design, or they may not. The key thing here is extracting the impact of a single variation by having clear-cut control variants and not presenting too many different features to a user at once. You need to be able to clearly identify which change in the application caused the different user behavior. The second key thing is that there must be a significant enough amount of data to truly measure and understand the impact of changes. If there's a large number of variants tested, or the change in user behavior is small, or the variants are not tested on enough users overall, the data may not be meaningful enough to implement a change. The rest of my team will describe how we handle these challenges at Test Lab a little later. First, Chelsea will describe some of the existing solutions on the market and begin to introduce Test Lab and where it fits in.
Looks like I'm up. I'm Chelsea, and I'll be leading you on the exciting journey through some of the existing solutions for A/B testing. There's a wide range of A/B testing platforms, and while there is a market for specialized what you see is what you get editors like VWO, which allow users without web development experience to perform limited testing of purely aesthetic changes, our focus was on platforms that offer a wider range of testing, even though they do require developer expertise. In other words, you're going to need some nerds like us on board. Within the category of A/B test suites geared towards companies with a skilled development team, there's a broad range of products, the most basic of which are bare-bones applications that expose APIs for creating and retrieving experiments from the command line. However, platforms that are this basic are not widely used. At the other extreme are options like Launched Darkly, which offer not only APIs, but SDKs for easy integration with client websites, administrative user interfaces for managing experiments, and that either provide or support existing data analytics services. Platforms in this category are often costly and externally hosted. Hosted platforms like this can be a fine option for large companies with existing data collection and the financial resources to spare on third-party hosted solutions. However, they're out of reach for smaller companies without data analysis already in place and in need of a self-hosted option. Open source self-hosted platforms that fall more in the middle of the road are relatively sparse and tend to either fade away or experience rapid growth and become fully featured managed options, as just discussed. Within the limited self-hosted category, two key options are Growthbook and Unleash, both of which offer some of the same key features as the larger players, but also feature open source deployment options. These solutions inspired some of the key features and functionality of Test Lab. However, neither of these platforms is well suited for a site that's not already equipped with a robust data analytics platform. As you can see, one key feature that sets Test Lab apart is our ability to collect and store event data. Our product is targeted towards clients that have not yet started data collection, or who want or need the ability to host all of their own event data. Test Lab provides our clients the flexibility of an open source, locally hosted platform, but without the burden of incorporating massive analytics infrastructure. While we do require our clients to integrate API calls into their own event listeners in order to send data to the event database, this is a trivial task and provides our clients total flexibility over their event tracking, as well as a little job security for developers like us. While our primary focus is experimentation, Test Lab also offers feature toggles, which automatically enroll 100% of users in a given feature, and feature rollouts, which allow our clients to enroll a custom percentage of users into a given feature. However, neither feature toggles or rollouts include event data collection. Now that we've gotten a sense of the overall landscape of A/B test platforms, let's move on to a basic overview of our implementation. Test Lab architecture consists of 4 key components: an administrative user interface built with React that facilitates creating, editing, deleting, and viewing current, scheduled, and past features, as well as viewing experiment data. A Node Express backend server that exposes API endpoints for creating, retrieving, editing, and deleting feature configurations, as well as collecting and retrieving event data for analytics. A Postgres database for persisting data, including feature configuration, user block allocation, and event data for experiment analytics. And finally, native SDKs for Node, React, Ruby, and Python for easy integration of our platform into both server and client-side rendered applications. We will do a deep dive into each of these components, but this is the general outline of test lab infrastructure. Before I begin discussing the specifics of our architecture, I do need to address one key implementation challenge that we faced: ensuring that users of our client site are only enrolled in one experiment at a time. If users are enrolled in multiple experiments concurrently, it would be impossible to determine whether any difference in tracked user behavior was the result of the variant being evaluated or the combination of variants to which the user was exposed. In other words, if you were simultaneously running a test to see if a blue button made users more likely to click that button, and another test to see if a photo of actor and heartthrob Ryan Reynolds next to a button made users more likely to click that button, some users would see only the blue button, some users would see only Ryan Reynolds, and some users would see both, and that would be chaos. You would not be able to distinguish whether it was the button color or the photo or the combination of both that caused users to click more, and we would have failed at our job of providing you with useful data. This would not empower our clients to make informed decisions even after the results were compiled. In order to ensure user enrollment in experiments is mutually exclusive, meaning if you're in the Ryan Reynolds test, you only see Ryan Reynolds, not the blue button, and if you're in the blue button test, you only see the blue button and not Ryan Reynolds, we developed a user block strategy. User blocks track assignment of users to experiments, where the available pool of users is segmented into 20 chunks, each representing 5% of the user base. Each of these chunks, or user blocks, is permanently assigned to exactly one experiment for the duration of that experiment, ensuring that users in each user block are only exposed to one experiment. As soon as an experiment concludes, all user blocks that were allocated to that experiment are released and may be reallocated to upcoming experiments as needed. Alison will walk through the logic of user blocks in more detail when she discusses our SDKs, but this should be enough of an explanation of user blocks to get the discussion of our administrative user interface going. So let's do it. At its core, the administrative user interface, or admin UI as the cool kids say, is basically a CRUD application designed to let clients create, read, update, and delete features with ease and a touch of glamour, at least as compared with command line API calls. But the admin UI also features additional functionality to ensure client success with experiment creation. Among the additional functionality included in our admin UI is a tool to ensure that our clients do not overbook experiment user blocks. As our clients select dates for their experiments, the admin UI calculates the maximum percentage of users available for experiment enrollment during that period and prevents our clients from scheduling experiments that require more user blocks than are available. Additionally, as our clients view their existing features, they can also pause features. Perhaps they've discovered a pesky bug that needs fixing, or they realize their competitor are having a big sale that might disrupt their experiment data for a day or two. Our admin UI allows our clients the ability to pause and resume features with ease. Clients can also delete features entirely, though this does result in permanent removal of all data related to that feature from the database. So maybe not something you want to do with your Ryan Reynolds experiment. We've also tailored our feature editing options to ensure maximum flexibility when editing upcoming features that are not currently ongoing, including the ability to modify names, descriptions, start dates, end dates, and user enrollment percentages where relevant, as well as the value, weight, and quantity of variants for experiments. However, in order to ensure that our clients do not make changes that damage the integrity of their data for currently running experiments, our admin UI limits our clients' ability to make destructive changes to ongoing features. Once an experiment has begun, the start date may not be altered, variants may not be added or removed, and variant weights may not be changed. Clients still have the flexibility to alter the name, description, end date, and overall percentage of users site-wide that are exposed to the experiment, as well as the variant values, because hey, typos happen. Our admin UI is designed with client success in mind, and we do our best to ensure all features and experiments run smoothly and provide valid, useful data. Finally, For current and past experiments, our admin UI allows our clients to view in progress and final results, respectively, of the data collected from their experiment. The visualization of data helps illuminate the difference between variant performance and guides our clients towards making successful decisions when experiments conclude. That about sums up the admin UI. I'll hand this off to Alison to discuss more of the test lab architecture.
Thanks, Chelsea. Let's kick it off with the test lab backend server, which plays several key roles within the test lab application. First, it exposes API endpoints for creating, editing, deleting, and retrieving feature data. Also, creating and retrieving user data to be used during the experiment data analysis. And finally, storing and retrieving event data from experiments. The test lab backend server also ensures the integrity of data sent to the test lab database. As Chelsea mentioned in the previous section, the test lab backend server also assigns user blocks to each experiment to ensure that no more than 100% of users are enrolled in an experiment at any given time. This also ensures that users do not move from one experiment to another. Finally, the test lab backend server keeps track of the last time that the feature data was modified, which, as you'll see in a few slides, supports the efficient retrieval of feature data by the SDKs. It's important to note that developers have the option of using the admin UI and SDKs to interact with the test lab backend server, or they can use the API directly. And we do provide extensive API documentation to support that option. Persistent data is stored in the test lab Postgres database. The database stores several categories of data. First, feature configuration data for toggle, rollout, and experiment features, including a feature's name, description, and the proportion of users enrolled. We also store variant configuration data for experiments, including a variant's name, value, and the proportion of users in a given experiment that will experience that variant. User data is stored for users enrolled in experiments, including a unique string identifying the user's IP address, and the variant that the user experienced. We capture and store event data posted by experiments, including the time of the event, the user triggering the event, and the variant the user experienced when triggering the event. And finally, we keep track of user block data that represents which blocks of users are allocated to which experiments at a given point in time. So how do we use this data to actually deliver specific features to a particular user of our client's application? Well, test lab includes Node, React, Ruby, and Python native SDKs that help a developer translate the feature configurations made in the admin UI into their application code. The SDKs enable three main functions. The first is retrieving features, where the test lab SDK client retrieves up-to-date feature and user block information from the backend server and uses that in the second step, which is evaluating features. The test lab assignment logic is used to evaluate the feature for each request. And finally, we deliver a variant. Based on the feature value, the appropriate variant is rendered for a specific user. So let's walk through each of those three steps. First, retrieving features. The SDKs use polling to keep the feature configuration up to date. The first time the SDK client makes a request to the backend server, the server reaches out to the test lab database to retrieve the current feature and user block configuration. And that data is returned to the server and then to the SDK client. The SDK client then stores an in-memory representation of the current configuration of features and user blocks and uses that data to determine the value of features for a given user. And we'll talk about that process in just a minute. As I mentioned a few slides ago, the test lab backend server keeps track of the last time any feature data was modified. So the next time that the SDK client reaches out to the test lab backend server, if there have been no modifications, then the server just returns a 304 not modified status code and does not need to reach out to the database for new data. The key takeaway is that new feature data is only returned if it has been modified since the last request. You may wonder why we use this strategy rather than setting up server send events or WebSockets, and Sarah will talk about that a bit in the next section. But first, let's talk about evaluating features. The SDKs determine whether features are active, and let's start with toggles and rollouts. Toggles are simple. We check to see whether the feature is active or paused, and we looked at the start and end date. If the feature is active and the current date is within the start and end date of a toggle, then the SDK returns true and the feature is active. Otherwise, the SDK returns false. Rollouts are a lot like toggles, but with an extra step. We still check to make sure that the rollout is active and that we're within the start and end date range. But rollouts are only active for a particular percentage of users. So how do we determine whether a rollout is active for a user? Well, both rollouts and experiments, as we'll see on the next few slides, rely on using a hashing function to convert a unique string to a uniformly distributed value between 0 and 1. In the case of a rollout, the unique string is the user ID concatenated to the name of the rollout. If the hash value of this string is less than the rollout percentage, then a rollout is active for a given user. Let's take this a step further and see how feature evaluation works for the last feature category, which is experiments. We just saw that rollouts and toggles return true or false. In other words, they're either on or off for a particular user. However, active experiments do not return true, but instead return the particular variant that should be rendered. Let's walk through how this works. We start with the same checks to ensure that an experiment is active and within the start and end dates. But the next step is different. We use our hashing function to hash our unique user ID to a value between 0 and 1. And we use that value to determine which user block this user is assigned to. You may recall from Chelsea's discussion that user blocks are our way of determining which blocks of users are assigned to a particular experiment. So based on the hashed value of the user ID, we identify the user block and we check to see whether the experiment is active for this user. If not, we just return false. But if so, we return the appropriate variant based on that hashed value. In the example here, we'd return variant 1 30% of the time, variant 2 30% of the time, and variant 3 40% of the time. Let's take a closer look at how that works. As we just discussed, user blocks are critical to experiment evaluation. And once we've determined that a user is enrolled in a particular experiment based on the user block assignment, we need to determine which variant to serve. And we do this based on the variant weights. In the example here, there are 3 variants, again, with weights of 30%, 30%, and 40%. Let's suppose the hashed value of our user ID is 0.54. We know that we're in the 0.5 to 0.55 user block, which in this example corresponds to experiment 2. But how do we know which variant to return? Well, we break up the user block into segments based on the variant weight. Hashed values that map to the first 30% of the block would be served variant 1. Values that map to the next 30% of the block would be served variant 2, and values that map to the last 40% of the block would be served variant 3. In our example, 0.54 would fall into the last segment and would be served variant 3. Now that we've looked at how the SDK retrieves feature configurations and how it uses assignment logic to serve a particular variant, let's see what that looks like in the code. So based on the return value, the appropriate variant is rendered. In this example, we have a snippet from a simple Node Express app, where we use the TestLab SDK client to retrieve the value of my experiment for a user with a randomly generated user ID. The developer would include logic on what they want to render depending on the value of the experiment. In this case, if we return the value of Ryan, we render Ryan Reynolds on our ice cream shop page, and otherwise we display the default page with no image. If the variant weights are 50-50, then you would expect that about 50% of users that are enrolled in this experiment would see Ryan Reynolds, and the other unfortunate 50% would miss out. Now that we've seen the process of using TestLab, from creating experiments to ultimately rendering specific variants, Sarah's going to walk you through some of the engineering decisions we made while creating TestLab.
Thank you, Alison. Designing TestLab led to some interesting decision points. I'm going to share some of those decisions, the trade-offs we made, and the logic that led TestLab to become what it is today. The first set of decisions relate to the architecture of Test Lab. We chose to have a self-hosted platform that stores data in a PostgreSQL database and has an API that is easily accessible outside of the admin UI. First, let's discuss our decision to have Test Lab be self-hosted. We mitigated the complexity of a self-hosted solution by Dockerizing Test Lab, and using a self-hosted solution allows the opportunity for customization, complete control over data, and a lower cost. The majority of options on the market are managed A/B testing with client-side rendering. One advantage of managed platforms is that they can be easier to set up than a self-hosted platform. However, as the display documentation shows, Test Lab has mitigated this difference in setup complexity by Dockerizing our platform and providing clear documentation that explains how to deploy Test Lab using a Docker image. Now let's discuss the benefits of self-hosting. A self-hosted and open source application allows customization of code to fit your specific needs. For example, if the developer always expects features to last 2 months, they can add code so that the add feature form always defaults to 2 months. A managed solution does not provide access to the source code, so this sort of customization would be impossible. Another benefit is owning your own data. This can be important if you want to keep your data on-premise or if you have specific data retention or compliance requirements. Finally, the self-hosted solution has a cost benefit. There is no cost to download the software. A self-hosted platform allows you to scale your platform as your company growth requires. We minimize the shortcomings of a self-hosted platform by making installation as easy as possible and thereby gaining a solution that allows customization, control over the data, and cost benefits. Another major decision was which type of database to use. We needed to store data about features, users, and events, for example. Some options were a time series database, NoSQL, or a SQL database. The time series database would allow us to store event data with more granularity, but we decided it was overly complex for our needs since the focus of analysis is on the aggregate of the data. NoSQL databases are ideal for data that is not structured or could have a changing structure. We chose Postgres, a SQL database, because our data needs to be structured. We rely on the relationship between the user and event data for a data visualization feature, for example. Feature configurations require specific data types to work properly with the SDK and admin UI. The rigidity of Postgres adds an additional layer of validation on top of the validation in the admin UI and the backend. Other benefits of a SQL database are data consistency and reliability. The next decision relates to the API design. While building our API, we tried to make it so that using the admin UI is not required for the really big nerds. This meant exposing more of the API interface than it is needed by the admin UI. One downside of this is greater potential for the developer to use the API incorrectly, aka nerds who think they're bigger than they really are. Currently, we have more validation present in the front end to prevent user errors than in the back end. We felt that the flexibility of allowing the developer to interact with API outweighed the potential downsides of a developer using the API incorrectly. We tried to mitigate this risk by providing extensive API documentation, as you can see on the left. We also made decisions related to the design of Test Lab. We chose to implement context with flexibility, limit users to one experiment at a time, and pulling for SDKs to retrieve the current features configuration. First, let's look at how we chose to implement context. Context is the internal memory representation of the factors that influence which features and variants are active and can be used to allow a user to experience the same variant across multiple requests and across multiple sessions. It is implemented within the SDK. Earlier, Alison explained how the user ID is hashed to determine the active features and variants for that user. When implementing context, we chose a flexible approach that defaults to a random UUID assigned to the user ID in the context. The context can also be changed using the update context method, passing a new value for the user ID. This new value can be any unique value. You could keep it the default random value, or change it to a session identifier or an email, for example. The random value is ideal for features that are not dependent on user identity or behavior, such as a button color or banner placement. This ensures that the results are not affected by any systematic differences between users. The session identifier is best for features that are dependent on user behavior during a single session, such as the effectiveness of product recommendation. This ensures user behavior is consistent across control and treatment groups. Using an email or login may be appropriate for features dependent on user identity or behavior over time, such as a personalized email marketing campaign. This ensures that the user receives the same variant over a longer time frame, and that the differences in user behavior are from the feature and not user variability. These are just some of the options you could implement to utilize the flexibility in Test Lab's design. Next, let's discuss why we chose to limit users to only one experiment at a time and how we implemented this feature using user blocks. If users are allowed in multiple experiments at the same time, then to determine the effects of each experiment would require a multivariate analysis to determine the effects of the given feature. This is not only more complex, but requires a larger sample size, which would increase the time and resources needed for the experiment. It would also create a higher risk of false positives and overfitting the data. Limiting users to one experiment avoids those risks and is more appropriate for our use case with a more modest user base. We accomplish this with user blocks, which, as explained before by Chelsea and Alison, are created by blocking the users into percentage groups. The main goal of user blocks is to limit users to one experiment. The hashing of user ID to user block is deterministic, so each user ID remains in the same user block until the user ID changes. Also, once a block of users is allocated to an experiment, it remains allocated to that experiment until the experiment finishes. This allows us to split the experiment across separated user blocks by dynamically assigning the experiment to any user blocks that are unassigned when the experiment begins. When designing the user blocks, we chose to use 5% groups, which allows some granularity, allowing up to 20 concurrent experiments. Having a coarser granularity will make it more likely for experiments to reach statistical significance by having larger sample sizes. Designing user blocks to allocate experiments to fixed groups within the user base allowed us to have multiple experiments running at the same time while avoiding the unnecessary complexity of multivariate analysis. Now, let's discuss our decision to use polling to keep an up-to-date in-memory representation of the feature configuration. Alison described earlier how the SDK uses the feature configuration to determine which features are active. We considered 3 options to keep it up to date: polling, the option we chose to implement, server-side events, and a WebSocket. We chose polling for its simplicity, compatibility, and efficiency. WebSockets and SSE provide real-time updates to the data. Since we don't need to immediately update the feature's configuration, we can use the simpler polling option that updates the data at predefined intervals. The interval can be changed to better fit your use case. WebSockets and SSE would require server-side configuration, whereas polling is widely supported by all modern browsers, so polling has better compatibility. Finally, polling is more efficient because the server only responds with new data when the feature configuration has changed, instead of keeping the connection open like an SSE or WebSocket. Polling was a clear choice for updating the feature configuration in an SDK because it is simple, compatible, and efficient. Another attribute of Test Lab that we are excited to share with you is the full test suite. We are proud to have developed the API concurrently with the test suite, which allowed us to ensure that new code did not impact previous functionality. The test suite has 90% coverage. It is written in Jest and uses the super test library to test the API routing. Our tests are written as unit tests to test each API route. They include setup and teardown to avoid affecting real data. Tests for each API endpoint includes testing to confirm it responds, accepts data, and returns data in the correct format. This includes testing that errors return the correct status and message. Some entities should also accept using default values when creating or updating certain values. We also included tests that ensures the API accepts using the default values. Finally, we wanted to ensure that the SDK received a 304 status message when there is no new data. Now, let's explore some ideas we had for future work to continue to improve Test Lab. We chose to segment users into 5% chunks. Based on Test Lab user feedback, we might change this to smaller chunks. One option we considered was adding routes that allow the user to choose from a range of block sizes when using the SDK or API. Another feature that we are excited to develop is adding an SSE for real-time updates on the status of features. We envision a dashboard where we display the experiment health metric on current experiments, making it easier for an admin to check the experiments are performing as desired. Another major feature that we are looking forward to developing, forward to exploring, is adding some statistical analysis. We chose to start with a visual representation of the data, as well as providing API access to the raw data. This provides flexibility in how the data is analyzed with your preferred metric. However, there may be some value in providing some simple measures of statistical significance for commonly used types of experiments. In addition, we believe it could be useful to allow users to convert the winning variant to a toggle or rollout. Our roadmap continues with other functionality we are excited to develop, which leads to our next segment, questions from the audience. We are now opening the floor for questions, and Abbie will read those from the comments section.
All right. So here in the comment section, or I mean the question section, we have a question from Mai. Does user blocking take into account active versus no longer active users? Do users get shuffled for blocking purposes? Assuming that user IDs are assigned incrementally at the time of registration, I would also assume that older users are more likely to be no longer active. If one experiment's assigned to, say, the bottom 30% based on user ID, wouldn't they be unproportionally likely to contain non-active users? Maybe someone wants to take that. That was a long one, and then I'll read the second section. I feel like it might be helpful if I go back to the user block slide.
So one of the things we talked about was how the flexibility in how we assigned users. And I think that you're thinking about users in a way that it's like a user signs up for an account and then they have a user login and they have an email and password to log in. And that's one way that you could assign a user to within the system. However, the default is using a random UUID. So when we look at a user ID being in the bottom 10% or in the top 30%, it is random for that random UUID. Plus the user ID is hashed from when we get that value, we hash it from the value that you provide. So for example, if you decide to utilize their session identifier or their email login, which includes when they were signed up, then that value would be hashed. So it's still assigned to a random value between 0 and 1. Does it take into account if older users are no longer active? So again, that's the flexibility of it. The original setup is using a random default value, in which case, when you go to the website, then you would be assigned a value and you would be considered an active user because you're using it. However, if you are using email logins or system identifiers, that's added functionality that you would have to set up on your end of it. And how would this affect the 100% number? So Abbie, can you read the rest of the question?
Sure. Also, how does sectioning or blocking work for newly signed up users, as this would affect the 100% number since the number of users improves?
So I think maybe a point of confusion is that we are not starting with a quantity of users. So essentially, what we're doing is taking a value, which can be a UUID or an email or whatever our clients select, and putting that value through a hashing algorithm. And what a hashing algorithm does is it basically randomly assigns a numerical value. So it's not looking at like, okay, you have 100 users today and we're going to take the first 5 users. It's literally just an equation. And statistically, hashing algorithms are designed in such a way that the outcomes, the numbers that they produce, should be evenly distributed. So it's really kind of irrelevant how many users you have. There's a point at which you might have so few users, if you've only got 10 users, you might not get really even distribution. But we have selected hashing algorithms that are sort of designed for the user base that we're targeting. And so it's less about the overall volume of numbers and more about kind of where this hashing algorithm assigns what value it assigns to that input. So I hope that answers your question, and feel free, to reach out to any of us individually if you have further questions, but I think we spent maybe a little bit of time answering this one already. So
yeah, thanks, Chelsea. We have one other great question here in the chat, and then we'll wrap up. Are there any perceived scaling issues with your application as the user count increases? And again, I think that some of this goes back to that confusion on user count and how the user blocks work, but can anyone answer that?
Yeah, I think it's the same answer basically. The hashing algorithm, essentially every time a user visits our client site, whatever ID, whether it's the ID that we generate or the ID that they've selected to use, will go through that hashing algorithm. So, there's not really any anticipated scaling issues. This is actually the hashing algorithm method of doing this is something that some of the larger products that we looked into also use. So it's not an uncommon solution even for really large platforms. So there really shouldn't be any scalability issues. Again, unless you're looking at a site that literally has like 10 users, in which case our maybe wouldn't be as effective. At least that's.
And the other key piece of. Oh, sorry. Go ahead. The other key piece of our solution is that it is self-hosted. So ultimately, the computing resources are up to our client who, who basically launches our products on their Docker. All right, and then we have just one final question from Serjan himself. Why is Ryan Reynolds so good looking?
Wow, Serjan, that's an excellent question. Definitely one for the ages. I don't think even we at Test Lab can answer that, but I do think that's a nice note to end things on. So thank you all so much for attending our presentation, and we hope that you enjoyed it.